I will be presenting our work SparseDet, improving sparsely annotated object detection with pseudo-positive mining. Deep networks need clean data that includes exhaustive bounding box annotations and correct category labels. Let's see what happens when we have missing annotations by progressively dropping annotations from Pascal dataset and training detectors. As we can see, there is a noticeable drop in performance as annotations are removed. Such label imperfections can be because the annotator didn't annotate repeated instances, out of vocabulary instances, or occlusion. This problem of training models with missing labels is called sparsely annotated object detection. First, let's see why training with missing labels hurts the model performance. Consider an image with three objects, out of which only one is labeled. To train an object detector, we consider all proposals with IOU greater than 0.5 as positives, which look like this, and all the proposals with IOU less than 0.5 and greater than 0.1 are treated as negatives. Since we are missing a few annotations, we get negatives on potential positive boxes. If left unattended, these regions, which should have been positives, will be penalized as negatives. Our goal is to avoid penalizing the detector for predicting proposals on these image regions. Let's go over our approach now. Following popular self-supervised methods, given an image, we compute an augmented version of this image. We use a backbone to extract two sets of features, FO and FA, for the original and augmented images. Let's call them original and augmented image features. We concatenate these features and use a common RPN to get proposals. This RPN takes in both features and is able to predict a common set of proposals utilizing both views of the image. We do a pseudo-positive mining on these RPN proposals to get potential positive proposals BN and remove them from the list of RPN proposals to get the remaining proposals B. We use the boxes B along with FO to perform ROI pooling and use the detector head to get the final predictions. We apply a supervised loss using the existing ground truths. We use the same ground truths to apply standard RPN losses on B. We then use the boxes B along with FA to extract the final predictions for the augmented features. We use the predictions from the original features, append them to the ground truth, and apply a supervised loss for the augmented feature predictions. For BM, we extract the detection head features of the original and augmented features for the corresponding regions and apply a self-supervised loss. Since we don't have a class label for these masked boxes, we use MSE loss as the self-supervised loss. These regions would have been treated as negatives while training the detection head. In our method, we prevent this from happening. It should be noted that all the networks with the same color share weights. Moving on to some quantitative results. The x-axis here is sparsity in data and y-axis is MAP. Out of 3 splits on COCO, we show results on 2 splits. It can be noted that we improve over the existing work in all cases and are especially effective in high sparsity settings. Similarly, here we show results on 2 splits on Pascal VOC dataset. Again, we show improvement across splits and sparsity and show that we are especially good at high sparsity level. Sparsity in the annotations can occur in two ways. It can be sparsity in the labeled regions, where a few regions are labeled and some unlabeled, or sparsity in labeled images, where a few images are completely labeled and a few are not. Sparsely annotated object detection methods cannot deal with image sparsity, while semi-supervised object detection methods cannot deal with labeled region sparsity. Our method, on the other hand, can deal with both. To demonstrate this, we propose a new setup which consists of sparsity from both these types. In this SSL plus SAOD setup, the unlabeled set is VOC 2012 and the labeled data is VOC 2007, but with varying levels of sparsity similar to split 5. Here we show some qualitative results. First, we visualize the output of pseudo-positive mining step in our approach, where we avoid penalizing the network for predicting outputs on regions which have objects but missing ground truths. The red boxes are the available ground truth, and the white boxes are regions corresponding to missing annotations, which would have been considered as negatives. Our approach removes these regions from the set of negatives. We also show some outputs to compare between vanilla model trained on sparse data, the top row, and using our approach on the same data shown in the bottom row. Our method is able to detect more objects correctly. Thanks for listening.